like, it's just, this is the simplest it can get. So it will keep on getting difficult. So I gave you the test because, yes? So I gave you the test because, like I told you, this course is like very intense, like mathematically. So I gave you a cheap test so that at least it will compensate when. So we are going to start the class with the discrete time Fourier transform. So for the discrete time Fourier transform, we are trying to get the Fourier transform of a signal at discrete points in time. So at specific points in time. So when given a signal, the signal is going to be divided into different chunks, so different intervals, and we are expected to get the Fourier transform of that signal at the different time intervals. So this division, F1, F2, F3, and so on. So we are dividing it into, this is the signal in general, but we are dividing it into different chunks. Then we'll find the Fourier transform at that particular time instant. So for the formula for Fourier transform of DFT, discrete time Fourier transform. So this is the formula. So where f sub k. So remember that we are dividing the signal into different into time intervals. So into discrete time intervals from k is equal to 0 to the last value, which is n minus 1. So that's why you have this f of k here. Then is a summation. So we are going to be doing an example in order for you to know how to go about this summation. Then this is to find the inverse discrete time Fourier transform. So it's just the formula for the both of them, the DFT and the inverse is kind of similar. It's just that here is the Fourier transform. So here is a Fourier transform. So f of j is the is this breaking down we did. So breaking down the signal into different time intervals. So looking at the amplitude. So this is the formula to actually get the DFT. So in this for this DFT, the omega naught, which is the angular frequency, is given by 2 pi divided by n. So omega naught is 2 pi divided by n. So remember in the continuous case, in the continuous time case, the omega naught was 2 pi divided by t. But in the case of the discrete time, is 2 pi divided by n, where n is equal to the number of samples. So this is, so let me just write it. So f of k, which is the discrete Fourier transform, is the summation from j is equal to 0 to n minus 1 f of j exponential minus I k omega naught j. So where k is from 0 to n minus 1. So this is for the for the DFT. So this is the formula for the DFT. So remember that omega naught is equal to 2 pi over n. So we are going to be doing an example. So for this formula, so here there is a factor here of 1 over n. So this factor, it can be in either of both. So it can either be in the formula for DFT or in the formula for the inverse DFT. So it's not compulsory that the inverse DFT should have 1 over n. So it can be in either of them. So we are going to talk about some fundamental terms. So before we actually start to do an example of DFT, so we'll talk about the Nyquist frequency. I'm sure you would have heard of it, or you have done something about the Nyquist frequency. So the Nyquist frequency is the highest frequency that can be measured in a signal. So because you are dividing the signal into different time, into different chunks, into smaller chunks. So you want to be able to make sure that the frequency you are operating is within the Nyquist frequency, and the Nyquist frequency is given by half of the sampling frequency. So that's the formula to calculate the Nyquist frequency. So the Nyquist frequency is also called F max. So it's simply the highest frequency that can be measured in a signal. Then as we have the Nyquist frequency, which is the maximum frequency, we have the minimum frequency. So the minimum frequency is the lowest frequency that you can detect in a signal, while the Nyquist frequency is the highest frequency that can be detected in a signal. So, and it's the inverse of the sample length. So we'll do an example. So for instance, so given this example, so if you have 100 samples of data, so 100 samples of data simply means that n is equal to 100. So n is equal to 100 samples, and your sample frequency is 1000 Hz. So the sample frequency f of s is 1000 Hz. So we want to get the Nyquist frequency. I'll give them after the class.
Oh, class first. Come here.
I'll give you after the class.
After the class,
Come and collect it.
What of the solution?
Today. The test.
Yeah.
Maybe I'll upload it on.
Okay. So, and I'll be quick. Oh, we actually did have who are you asking? That's so good. How finish this? Well, somebody advised that was not there. Time for this. Because here I say I work like okay. The convention like next one. So at least the first step, if I will need okay, you take 1 hour, I take 1 hour. Yes, take care.
Okay, sir. So if the sampling, so if n is equal to 100, so simply means that you have 100 samples. Then the sampling frequency is given by 1000 Hz. So we want to get some information about the signal. So if you want to get the sample interval, so this is the sampling frequency, and this is the sample interval. So the sample interval is just in time. The unit is in seconds. So the sample interval is simply the inverse of the sample frequency. Then, if you want to get the total sample length, so the total sample length, so for instance, maybe this is the signal that you're working with. Then you want to get the total sample length simply means the total time duration for that particular signal. So the sample length is just given by n times 1/f of s. So when you do that calculation, your answer is going to be in time, in seconds. So the sample length is in seconds. So the sample length is given by n. So n, where n is the number of samples and f of s is the sampling frequency. So it can also be given by n times the t. So where the t is the sample interval. So the t can also be the sample interval. Then the Nyquist frequency. So we already talked about the Nyquist frequency. So it's the highest maximum frequency that can be detected in the signal. Then the Nyquist frequency is half of the sample frequency divided by 2. So that's the Nyquist frequency. Then the lowest frequency, the lowest detectable frequency, which is F mean. The lowest detectable frequency is just the inverse of a sample type. So it's the inverse of the inverse of the sample interval. So the Nyquist frequency is half of this. Then the lowest detectable frequency is the inverse of this. So that's how to calculate these different measures. So we'll talk about FFT. So FFT is an algorithm that is used to calculate the DFT of a signal. So we are going to use two approaches. So we are going to use the Matlab approach. There is a Matlab function that you can just, once you just put in the Matlab, this function directly into Matlab, you'll be able to get the DFT. Then we are also going to do the hand calculation. So we are going to write the Matlab code. So basically, we are going to solve this particular question. So first of all, we are going to do it by hand. Then subsequently, we will do it using Matlab. So you should know the both of them. So you should be able to write the Matlab code, and you should be able to also do it by hand. So the question says that you should calculate, or you should find the DFT of this particular signal, and given these parameters. So generate 8 equispaced points with sample interval the t is equal to 0.02 seconds. Then you should plot the results as a function of the frequency. So so this is the formula to do it by hand. Then before we do that, we need to get some information about the signal. So we need to get the, from the question, n is equal to, what is n? Yes, for this particular question. Yes, so n is equal to 8, because the question says that you should generate 8 equispaced points. So, for instance, as I was trying to explain the other time, so if the signal is this, then the question says generate 8 equispaced points. So it simply means that you have 8 points. So maybe this is the first point, this is the second point, this is the third point, fourth, fifth. So sorry, this is the 0th point. This is the 0th point. This is the first, second, third, fourth, fifth, sixth, and 7th. So n is equal to 8. So if n is equal to 8, it will start from 0 and end at 7. So it's not ending at 8 because you are starting from 0. So if you count all of this, it's equal to 8. So the question is saying you should generate 8 equispaced points, and with a sample interval of 0.02 seconds. So between these equally spaced points, the sample interval is equal to 0.02 seconds. So all of this is equal to 0.02 seconds. So this is what we are given in the question. So we need to generate, first of all, we need to get the sampling frequency. So the sampling frequency is just the inverse of the sample interval. So the sample interval is 0.02 seconds. Then the sample length. So the sample length since the sample interval is 0.02 seconds, then you have 8 points. The sample length is simply n times the t, which is 8 times 0.02 seconds. So this is the sample length. So that means that the sample length is equal to 0.16 seconds. Then the next thing is the Nyquist frequency. So the Nyquist frequency is straightforward, is half of the sample frequency. Then the lowest detectable frequency is simply the inverse of the sample length. So it's the inverse of the sample length. So you can calculate it straight up. So we've gotten these parameters. So we now want to actually calculate the DFT now. So like I said, this is the formula to do it. So is a summation. So f of j. So f of j is simply the amplitude of the signal at a particular point. So we already know that we have 8 points. So to start the first thing you have to do when solving this question is to get f of j. So that's the first thing you need to do. So f of j, it ranges from 0 to 7. So you have f of j. So that means you need to calculate f of 0, f of 1, f of 2, f of 3, f of 4, f of 5, f of 6, and finally f of 7. So how do you calculate the f of j? So the f of j is going to be from the question. So this is the question, this is the signal f of t. So this is the signal f of t. So now, okay, let me write f of t is given by this particular signal. So you want to calculate f of 0. So f of 0 is simply 5 plus cos 2 pi 12.5. Then for f of 0, t is going to be 0. So t is going to be 0. So 0 plus sine 2 pi 18.750. So you calculate this. So for f of 1, you know, like what I said, you are starting from 0. So that means that f of 1, t is time. So that means that the next one is 0.02. The next one is 0.04. The next one is 0.06. So the next one is 0.08, 0.10, 0.12, 0.14. So that means that at F1, T is equal to T is equal to, yes, 0.02 plus sine 2 pi 18.75, 0.02. So at m is equal to 2, at f2, so this is 0.12. So we know that this the sample interval is 0.02. So we just keep incrementing the t by 0.02. So it's cos. So you can do the calculation. So F4 is equal to 5 plus cos 2 pi 12.5 0.08 plus sine 2 pi 18.75 0.08. Then F5, so this is F4. Plus cos 2 pi 12.5 0.1 plus sine 2 pi 18.75 0.1. Then F6 5 plus cos 2 pi 12.5 0.12 plus sine 2 pi 18.75 0.12. 5 plus cos 2 pi 12.5 0.14 plus sine 2 pi 18.57 0.14. So from your calculation, what's F0? F0 is 6. Thank you. What's F1? 6.041. So what's F2? Can you confirm this? Is it your calculator should be in radians? So please note your calculator should be in radians. So the pi. So pi is in radians. Yes, or except otherwise stated. So if there's nothing given, then just know that your calculator should be in radians. So putting your calculator in radians, then there's a pi on your calculator. So you can just put that pi symbol. So what's F1? Yes, F0 is 6. Yes, 5.1. Yes. So it's 0.7071. So what's F2? Yeah, 3. So it's pretty much straightforward. Just be changing this value in your calculator. So you don't need to keep retyping it. So what's F3? What's F3? Yes. 5.701. Then F4. 6. F5. 4.2929. Then F6. 5. Then the last value, F7. Okay. 4.2929. So, like I said, the first step in calculating the DFT is to get the F of J. So, based on the signal that you are given in the question, you can calculate the F of J. Then now, you will now calculate the DFT. So, given that you've known F of J, so for the DFT, you have F of K, where K is from 0 to n minus 1. So similar to how we got F of J, we need to get F of 0. So the DFT, so for DFT, we are calculating the DFT at discrete point in time. So you calculate at capital letter F of 0, F of 1, F of 2, and all of those. So these values are just the amplitude of the signal at different points in time. So we now want to calculate the DFT of the signal at different points in time. So for F of 0, so it's a summation. So it's a summation, and the summation is given by F of 0, E minus I, then K. So K is from 1 to n minus 1. So 0, then omega naught. So remember that I said omega naught is equal to 2 pi over n. So let me put 2 pi over n. Then J. So J is 0. Then so J is from, you are summing from 0 to n minus 1. So I'm coming. So F of 0. So it means that K is equal to 0. So like I said, you are the DFT at k is equal to 0, 1, 2, 3, 4, 5, 6, until you get to n minus 1. So we are doing for when k is equal to 0. So it's a summation. So the next one is going to be f of 1 e minus I. K is still 0. 2 pi over n. Then j is 1 now. Plus f2 e minus I 0. 2 pi over n. Then j is now 2. Because you're summing to 7. So n minus 1 is 7. So plus f3 e minus I 0 2 pi over n plus f4 e minus I 0 2 pi n 4 plus f5 e minus I 0 2 pi over n 5 plus f6 e minus I 0 2 pi n 6 plus f7 e minus I 0 2 pi over n 7. So this is k is equal to 0. So as you can see, you are summing from 0 to 7. So j is changing in the formula. This is j. So j is changing from 0, 1, 2, 3, 4, 5, 6, 7. So it's only j that is changing. K is constant. K is equal to 0. So like I said, if this is the signal, you want to get the DFT. This is k is equal to 0, k is equal to 1, 2, 3, 4, 5. So for k is equal to 0, k is constant. So the k is 0, 0, 0, 0 throughout. So it's the j, because you are summing over j. So it's j that is changing from 0, 1, 2, 3, 4, 5, 6, and 7. So you do this summation. So because exponential 0 is equal to 1, so this is simply f of 0 plus f of 1 plus f of 2 plus f of 3 plus f of 4 plus f of 5 plus f of 6 f of 7. So that's equal to 6 plus 5.701 plus 3 plus 5.701 plus 6 plus 4.2929 plus 5 plus 4.2929. So which is equal to 40. So remember that I told you that for this formula, the 1 over n, it can either be in the DFT or the inverse DFT. So if we decide to use 1 over n, then f of 0 is simply 40. N is 8 over 8, which is equal to 5. So now we do for k is equal to 1. I said, yes, but now instead of 0, you are replacing it with 1. Then it's just typically the same thing. Yeah, the reason why is because this is the formula for DFT. So I said that this is the formula for DFT to calculate the DFT of a signal. Either this or this. So I told you that this 1 over n is just an amplifier. So it can either be in this formula or in this formula. So it's just a scaling factor. So, but it's not compulsory that it has to be in the inverse DFT. So it can also be here. But one thing is that if you put it here, you cannot put it here again. So it's either here or here. So I decided to put it in the formula for DFT. It's just a scaling factor. It's just a scaling factor. So you can decide not to put it. So it's just a scale factor. So for omega naught, in this question, 2 pi divided by 8. So actually, 8, 8, 8, 8, 8, 8. So it's because of exponential 0 is equal to 1. That's why it sums up to this. Then you don't need, because this exponential 0, so exponential 0 is equal to 1. So it just remains this. So we need to do for k is equal to 1. So f1. So f1 is simply f of 0 e minus I 1 2 pi over 8 0 plus f1 e minus I 1 2 pi over 8 1 plus f2 e minus I 1 2 pi over 8 2 plus f3 e minus I 1 2 pi over 8 plus f4 e minus I 1 2 pi over 8 4 plus f5 e minus I 1 2 pi over 8 by 5 plus f6 e minus I 1 2 pi over 8 6 f7 e minus I 1 2 pi over 8 7. So we are on k is equal to 1 now. So remember we are getting to k is equal to 7. So for this one, f of 1 is equal to 6 because there's an exponential 0 here. So you just f of 0, which is 6. Then f of 1, you need to do this calculation. So can somebody do this? Remember, f of 1 is 5.001. So this is f1. So can somebody do this? This exponential, then multiply it by f1. So remember that your calculator should be in radians. Your calculator should be in radians. What's the I is a, yes, it's a complex. Your calculator have I. Does the calculator have I symbol? Yes. So you should just put in the I there. So because of this 1 over n. So when n is equal to 8. So when I get the results, your calculator have I. That's what Yeah, I said it can either be here or here. Huh? This 1 over n, this is the inverse. This is the inverse. But I said this 1 over n can either be here or here. Yes, it can be here. It can also be here. No. It can. So the 1 over n, it can either be in the DFT or in the inverse DFT. So if you decide to put it in the DFT, you are not putting it in the inverse DFT. So yeah, I just decided to put it in the DFT. So I want the result of this to be sure that you can actually do it. Can you put J? Because it can either be I or J. Let me see. Yes. So if you're, yeah, no, you can't be asked to do that because it's just it's kind of useless. So the question can either tell you to find the inverse DFT or the DFT. So it can't tell you to after finding DFT, then you should go back and find the inverse. Yes. 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 If you decide to leave your answer as, please keep quiet, everybody. If you decide to leave your answer as also fine. It's okay. Because this is just a scaling factor. So it can either be this 1 over n can either be in the DFT or in the inverse DFT, but not both. But not both. So yes. Yes. No, you can't be told to find both. You said if you are told to find both. Yeah. Yes. Yes. Okay, you don't always see that. I don't see okay. So please keep quiet. Please keep quiet, everybody. So this scaling factor. So if you read the notes, it says that I've already explained it in the notes. So the scaling factor of 1 over n, this 1 over n is just a scale factor. So it's just a game, it's just a constant that can either be included in the DFT or in the inverse DFT. So if you decide not to include it, then the answer is also okay, it's also fine. So you are also correct. So it's just a scale factor, and you can decide or not. You can decide to include it or not to include it. So in order to get this one, I think maybe you should find out how to use the calculator. But E minus E j theta is equal to cos theta plus j sin theta. And E minus j theta is equal to cos theta minus j sin theta. So you can just do your research on how to use this for your calculator. But if that is not forthcoming, then just use this formula to do that. So this is equal to, so let me just write it. So like I said, you can just simply use this one. Or you can do, maybe you should just do your research on how to just use this one expressly. Or you can just use this formula. So can you confirm using this formula? Yes, I do. Okay. And it's correct. Okay. So So we move to k is equal to 2. So remember that we are stopping at k is equal to 7. So f of 2 is equal to f of 0 e minus I 2 5 over 8 plus f1 e minus I 2 5 over 8 1 plus f2 e minus I 5 over 8 plus f3 e minus I 2 5 over 8 plus f4 e minus I 2 5 over 8 4 plus f5 e minus I 2 5 over 8 5 f6 I 2 5 over 8 So you can see the calculation. So it's really straightforward. For you just need to keep changing the value of K. So for K equal to for K equal to 1, now we have K equal to 3. Now we have like I said, is from K is equal to 0 to n minus 1. So since n is equal to 8, so you're going to stop at 7. So this is the DFT at this discrete point in time. So you can see that the calculation is very complex and very tedious. So that's why I brought in the Matlab approach. So like I said, you should be able to do the two. So I will just go through the Matlab approach to solving the problem. So you should be able to to do both. So you'll be able to write the MATLAB code, given a question to find the DFT, and you should be able to solve it. So when using MATLAB, so I will just run through the code. So this CLC, I know you've done a course on MATLAB, so I'll just adapt it to the question. So this CLC is just to clear the screen. So there's really nothing, it's not really doing much. So you can just commit it. So this second line, it says n is equal to 8. So in the question, the number of samples is equal to 8. So that's why you have n is equal to 8. Then the sample interval is given in the question as 0.02. That's why you have this 0.02. Then the sampling, f of s is the sampling frequency. So the sampling frequency is the inverse of the sampling interval. So that's why you have 1 divided by the t. Then the sample, total sample length is just, we found it at 0.16. So instead of writing t is equal to 0.16, you can just write t is equal to n multiplied by dt, and it's going to still be the same thing. So this is the line to get all those 4 parameters we talked about. Then let me go to this line. I'll come back to this shortly, but let me go to this line. So this is the Nyquist frequency. So the Nyquist frequency, like I said, is just the half of the sampling frequency. That's why you have it as fs divided by 2. Then the minimum detectable frequency, we defined it as the inverse of the sample length. And remember that we defined t as a sample length. So this is f min. So like I said, you should be able to calculate it on paper, and you should be able to also write the code. So the code is pretty much straightforward. And this t-span is to calculate the different time interval. So what this t-span is actually doing is that, remember that we want to get, when I told you that, given that the sample is, maybe this is the signal, then the sample interval in the question 0.02, then 0.04, 0.06, 0.08. So this t-span is to get that array of t values. So what this t-span is getting 0. So the formula is 0 to n minus 1 divided by f of s. Or you can say, instead of divided by f of s, it can be multiplied by the t. So it's still the same thing. So what this line simply means is that you should start from 0. So the first element is 0. Then then you are starting at 0. Then you are ending at n minus 1. Remember, n minus 1 is 7, but multiplied by the t. And the t is 0.01. So that means that you are starting at 0. Then you are ending at 0.02 times 7, which is 0.14. So in steps, you are starting at 0, ending at 0.14, but in steps of the t. So that's why you have 0.02 here, 0.04, 0.06, 0.08, 0.1, and 0.12. So that's what this line is actually all about. So let me type the line in Matlab. So we want to get, so like I said previously, this calculation is kind of complex. So you should be able to use Matlab or work it by hand. So yeah, I was trying to use Matlab to do the calculation. So like to do this calculation of f of 6 multiplied by this. So this is how to do it like in Matlab. So looking at this line, this span, so this is the array. Like I said, you are starting from 0. So this means that you should start from 0. Then you should end at, remember that our n is equal to 8. So n minus 1 is 7 times t, that's 0.14. So you are ending at 0.14. Then in steps of 0.02. So that's what this span is all about. Then this is to plot. So we want to plot the time as a function of y. So let me move to this line. So this line, looking at the code, what is this line about? That is the question. So this was the question we're given, that f of t is equal to cos 2 pi 12.5, then t span, because you know this t span is the values. So we essentially, in this particular line, we essentially want to get an array of these values. So multiplied by t span plus sine 2 pi 18.75 times t span. So that line came from the question. So this is the question. This is the signal. So look at the signal very well. Then look at what we typed in the code. So this is the signal. So you are translating the signal into Matlab code. So you are essentially just writing this, but in Matlab form. So in Matlab, this is how you represent times. Then pi. So there's a symbol called pi in Matlab. So this is the pi. Then this is the 12.5. Then this is the t, represented by t span. So remember, if the question should change, this formula too is going to change. So depending on the question, you cannot, yes, everything will change. For instance, if you are giving different values of n, so instead of putting 8, you put the value that you were given in the question. The t, you put the value you were given in the question. But this line will be the same thing. Then this line, it will change depending on the question. But this line is going to be the same thing. It won't change. So this line is going to change depending on the question you are given. Then this is to plot. So you are plotting 3 graphs. So that's why you have 3, 1, 1. Then, yeah, you are plotting 3 graphs. So the first graph we are plotting is the signal itself, f of t, as a function of t. So that's the first graph we are plotting. So this is it. So these two, the one I highlighted is the most important. So this value is the value on the x-axis. Then this value is the value on the y-axis. So you are plotting t, which starts from 0 to 0.14 as a function of y. Remember that y is the signal. So what you are essentially doing is that we are plotting these values as a function of t. So 0.02, 0.04, 0.06, 0.08, 0.1, 0.12, 0.14. So we are plotting these values. So there's a 6 here. So maybe this 6 and this 5.7. This 5.7. This is maybe 3. This is 5.7. Then F5 is F5 is 4 points. Then here. Then here is 5. Then 4 points. So this is what we are plotting. So we are plotting the signal as a function of time. Yeah, the question says this is to plot it in Matlab. So if the question says you should plot it, then you should plot it. Yeah, but this is the code to plot it in Matlab. You thought I said what? Yes, it's the question. So the way I plotted is not this particular one, is this particular one, because this is the question. We are just changing the values of t. This is the question. So it's just t we are changing so that we can plot the values. So this one that we calculated is the DFT. So we are plotting 3 graphs. We are plotting the original signal. Then we are plotting the DFT of the signal. So this is the signal itself. This is how to plot the signal itself. Then the next thing we are going to do is that we are going to plot the DFT. So we'll plot F0, F1, F2, like that. So that's what we are going to do next. So to plot it by hand is straightforward. To plot it by hand is straightforward. So what you need to do to plot it by hand is just for the x-axis to be n now, it's always with t. Like the discrete time domain, so it's 0, 1, 2, 3, 4, 5, 6, 7. So we'll plot the values of F0. So remember that it is an imaginary number. So this means that since it's an imaginary number, we are going to plot the real part. First of all, then we'll plot the imaginary part in the third graph. So that's why we need 3 graphs. The original signal, that's the first one. The second one is the real part of the DFT. The real part of the DFT. Then the third one is the imaginary part of the DFT. So, yeah. Against t span, we first of all divided t into different chunks. So you are plotting t, f of t. You are plotting t as a function of f of t. So, like for f naught, we got 5. So the array for the DFT, if we were to put it in an array, F0 is 5. F1 is 0. F2 is 0.5. F3 is 0.05. F4 is 0. F5 is 0.5. F6 is 0.5. And F7 is 0. So for the DFT, you know you have both real and imaginary. So you are plotting the real part as a function of n, and you are plotting the imaginary part as a function of n. Like for this f of 0, it only has a real part, it doesn't have an imaginary part. So that simply means that the imaginary part is 0. So for this one, it means both real and imaginary are 0. This one, the imaginary part is 0. This one, the real part is 0. So for this point, you are plotting 5. So maybe this 5, then this 0, this 0.5, this is 0.5 here. Then the real part is 0. For this one, you have 0 here, you have 0 here, then you have 0.5 here, then you have 0 here. Then for the third one, it's just the imaginary part you are plotting. So there's no imaginary here. 0, 0, 0. Then it's minus j 0.5. So maybe it's here. Then 0, j 0.5. Then 0. This one there is no imaginary 0 and 0. So that's how to plot it. So I want to see how to plot it in Matlab. So to plot it in Matlab, you first of all have to get the FFT. So this is the equation. This is the Matlab code to get the FFT. So all of these 3 pages we did, this is just the line of code that does it in Matlab. So this is just the line of code that does it in Matlab. Like this line of code here, the line of code here, this is what we did. This is what does it in Matlab. Then this one, this is what does it in Matlab. So divided by n. So remember I was telling you that this is a scale factor. So you can decide on whether or not to put it. So I've explained this line. Then here is just to get the frequency. So the reason why we are getting the frequency is that we are not actually plotting as a function of n. So we are not plotting it as a function of n. We are plotting it as a function of the frequency. So this is actually the frequency. So that's why you have this here. So it's not starting from 0 to n. So this is the frequency. So remember that the maximum frequency. So what did we get as maximum frequency when we calculated? So the maximum frequency. So this is the maximum frequency, f of s. So we are plotting from 0, which is the minimum, to f of s, which is the maximum. So this graph here is to plot from the minimum frequency to the Nyquist frequency. So it can either be the maximum frequency or the Nyquist frequency. So remember we said that the Nyquist frequency is the maximum detectable frequency in a signal. So we are plotting from the minimum to the maximum. Then this is know that our y is already the f of t. So what we are doing here is just to plot. What we are doing here is just to plot the DFT as a function of the frequency. So our x-axis is the frequency, then our y-axis is the DFT. So in real, meaning that is the real part of the DFT. So in this second one is the imaginary part. So this line of code here and this line of code, they are the same thing. It's just that here you are plotting the real part of the FFT. Then this is the code to plot the imaginary part of the FFT. So this is the Matlab code to solve the question. So like I said, it's going to change. The code is going to change depending on the question. So you have to really understand the code in order to be able to solve any particular question. So this is the code that does that. So I've already explained the code. So let me just copy and paste into Matlab. Yeah. Yeah. So those ones are not important. So he asked a good question. So for the plotting, it's just these two that are important. Plot this and this. So plot T span comma y. So this represents the x-axis, and this represents the y-axis. So all of this is just cosmetics. So the line weight is 2, the face color is black. So it's just cosmetics. So you don't need to be really interested in that. Then to plot, this is the most important here. So all of these are just extras. So this is the most important here in this line. So you don't need to. All of this is just saying that you should make it blue and the line weight should be 2. So when we do the plotting, so this is the plot. So this is the signal in the question. So remember that you have 8 points. N is equal to 8. So 0, 1, 2, 3, 4, 5, 6, 7. So you are going from N is equal to 0 to N is equal to 7. So you are plotting the real part of the DFT here. Then you are plotting the imaginary part of the DFT here. So this is basically how to solve the question in MATLAB. So like I said, it's compulsory for you to know the 2. So it's compulsory for you to know the 2. So that's very, very compulsory. But at least you should know the 2, but at least make sure you know 1 very well. Because if 1 fails you, maybe in the exam, maybe the other one would try to help you. But at least know 1, either to do it by hand or to use MATLAB. So yeah. That's what I'm saying, that it's compulsory for you to know the 2. It's compulsory for you to know the 2. Okay. Is it this subplot? No, it's not compulsory. So this semicolon is just to tell MATLAB that you should not print the results of the code of that expression on the screen. So that's what semicolon is saying. But if you decide not to put the semicolon, it's still correct. Like for instance, if I don't put, I didn't put the semicolon at the back of this one. So it's going to print the results of it on the screen. But if to say I put the semicolon, it's not going to print out the results on the screen. So the semicolon is not a big deal. It's not something that will give you an error. So the most important thing is that you should know the keywords. Like for instance, when you want to plot the real parts, this is the keyword you use. When you want to plot the imaginary part, this is the keyword you use. So how to get the different expression. So this is the keyword to get the FFT. So like I said, all of this calculation we did is just this line. It's just this line that does it in Matlab. So like I said, it's compulsory for you to know both of them. Stem is something as plots. So you can replace it with plots. So it's the same thing as plots. So instead of using stem, you can use plots. No, that's why I said that it's not compulsory, that this is the compulsory part. So the cosmetics is just, it's not compulsory. So this is like you are saying that this is, yes, this to label the graph. So this one is saying that this is the function as a f of t as a function of time. And this is the real part of the DFT. So if you want to really be very, you can say the real components of DFT versus frequency, then the imaginary components of DFT versus frequency. So when you eventually plot it, it's going to show the so real components of DFT versus frequency. So imaginary component of DFT versus frequency. So the title is important for you to actually know. So you should be able to do the two. So yeah. Yes. Okay, thank you for that question. So these subplots, the first one is 3, 1, 1. So this tree indicates that you are plotting 3 graphs. Then 1, that's the first of the 3. So the second subplot is 3, 1, 2. So what it does is that if this is the graph space, this tree means that it will divide the graph space into 1, 2, and 3. So this 1 is going to plot the f of t as a function of frequency at this point. Then this 3, 1, 2 means that you should go to the next plot. You should plot the real part as a function of frequency. Then the last one, 3, 1, 3. You should go to the third plot. Then you should plot the imaginary part as a function of frequency. So that's what it means. So are there any other questions? So this is the function. Yeah. No, if there's going to be changes, depending on the question, so this might change in the question. This might change. So these are just variable names. So you've done computer programming. You can decide to name this one. You can decide to name this one instead of n. You can name it number of samples. So it's just a variable name. Instead of the t, you can name this one as sample interval. So it's just a variable name that everything has to change. Then instead of f of s, you can name this one sampling frequency. Instead of t, you can name this one sample length. So this can change. So it's just a variable name, but this is a function. So this is the function that does the f of t. This is actually the most important line in the code. It's the function that does the f of t. So depending on, you can name this one f of t instead of y. So when you are doing the FFT, yeah, you put it as f of t. So it's just a variable name. So this particular function is to plot the signal. So when I'm plotting it in Matlab, so this is the function in the question. So we are just plotting 7 points. But this is not because we are getting the DFT at 8 points. So you are just plotting it at 8 points. 1, 2, 3, 4, 5, 6, 7, 8. So if you actually want to see the full signal, you can change this one to, you can change so we are plotting from 0 to 7. So if we plot from 0 to 100 in time steps of 0.01, so it shows a clearer form of the signal. So remember that this is a continuous time signal, but yeah, we are using 100 points. 100 points mean that it's from 0 to 100. So if I'm to use more points, maybe let me use, so this is giving a more clearer picture of the signal. So if I'm to use more points, let me use from 1000 in steps of 0.01. So we are I'm just trying to show you the signal. So it gives a more clearer form of what the signal is all about. Let me change it to, yeah, it's already on module. So the note is already on module. So if it's to steps of, so it's just to show you that depending on the way you plot it. So because we just have 7 points, so it's just to make it much shorter. the calculation shorter. So if you want more points, so this is the actual signal. So this is the actual signal. So it's showing that it is continuous. But because we're just using 8 points, that's why it was showing it in form of, in discrete form. So the most important thing, like I said, is that you should know how to write the Matlab code and know how to do it by hand. So know how to do the DFT by hand and the Matlab code, but you need to know at least one very well in order to solve it. So are there any questions? So the note is on module, so you can, and the code too is on module. So another thing is the power spectrum. So the power spectrum is just to get, is actually the same thing. So if you are asked to get the power spectrum is simply the DFT. Is simply the absolute value of the DFT. That's what the power spectrum is. So this is a DFT at 8 points. So if you are asked to get the power spectrum of the DFT, so it's to get, it's simply to find the absolute value square of the DFT. That's just the power spectrum. For instance, at f of 0, the power spectrum is 5 squared, which is equal to 25. At f of 1, the power spectrum is 0. At f of 2, the power spectrum is 0.5 squared, which is 0.25. At f of 3, what's the power spectrum at f of 3? What's the power at f of 3? Yeah? No. Yes. The absolute value square of the DFT. So you can square it first, but after squaring it, you get the absolute value. So 0.25. The power spectrum of this is 0. The power spectrum of this is 0.25. 0.25. So in the same way, you should be able to write the Matlab code for the power spectrum. So it's basically the same thing with that Matlab code. The only difference is this line. Please note it. That's the line that calculates the power spectrum. This line is bold. So the absolute value, so this function is the absolute value then squared. So this is how to do squared in Matlab. So please note it. Note it how to do it in Matlab and how to do it by hand. Yeah. See what? Yeah. Yes. So what it means, I did it here too in the first code. In the first code is also here. it's also the same thing that I did here. So yeah, it simply means you are starting from 0 and you are ending at 7 times the t. So this one is the t. So what this simply means is that you are starting from 1. So you are starting from 1. Then you are ending at, instead of ending at n, you are ending at n divided by 2. So this one is just, you are finding the DFT. So the DFT is from 1, 2, 3, 4. So it's from 1 to 4. So you can, this line of code is saying that you are only plotting the power spectrum at f is equal to 1, f is equal to 2, f is equal to 3, and f is equal to 4. You are not plotting the whole sequence of the power spectrum. So if you were to plot the whole sequence of the power spectrum, this will end at n minus 1. So you are plotting it and it will start at 0. It will start at 0 and it will end at n minus 1. So you are plotting f of 0, the power spectrum at f of 0, f of 1 till the last value, n minus 1. So that's what it simply says. Then this ABS is the absolute value. Then this represents the squared. So remember, power spectrum is the squared. You find the square, then you get the absolute value. Why did I? Okay. What did I change? Okay. Yeah. So it depends on the question. The question says you should plot the power spectrum from 0 to the last value. Then this is what you use. But if it says that you should plot from maybe 1 to 4, then the other code is what you are going to use. Any other question? This Matlab code is very important. So, which of them is for? No, they are basically the same thing. This is just the line that's changed. That's just the line. It depends on the question. It depends on the question.